Okay, so in this video we're continuing our section 6.1, and one of the one of the takeaways from 6.1 is that we can compute the Laplace transform from any basic functions here and get a formula. And so on the right here you see the section number, and we can use these then using some of the properties we're going to describe in just a bit to build the Laplace transform of other functions. Okay, so I should say while we're here that there are, when you're working on these problems, um, you should use the full table of transforms that's available on our class website. So let's take a look at it. You'll see that there's lots more available there. And in fact, some of these we haven't gotten to quite yet, but we will in time get through most of these, if not all. I think we'll probably be able to get through all. Okay, so you might go ahead and print this off if you can, just to keep it next to you while you're working on their homework. Okay, good. So now let's get rid of that and go back to our discussion here. So the main thing we want to talk about today are the properties of the transform. In particular, when does the transform exist? And so there are two issues for existence. One is whether or not the integral exists for which functions, and then the second issue is because we're integrating from 0 to infinity, we need to make sure that the function doesn't grow too fast, right? The exponential function needs to be able to quash it. Alright, so what is piecewise continuity? Here's an example. So piecewise continuous function is one that you can break into distinct pieces here and then have continuity on each distinct piece. And so the other thing to notice is that the types of discontinuity that are allowed at the breakpoints are only jump discontinuities. Okay. So for example, this would be something that's not piecewise continuous on the interval from A to B here because of this vertical asymptote right in the middle. Okay, so let's define that a little bit more carefully. Function is piecewise continuous, PWC, if there is a finite set of t's such that we usually set a equal to t naught and then b equal to t sub n, and then we have a finite number of t's in between such that f is continuous on each of those subintervals from ti to ti plus 1. And notice that these do not include the endpoints. So what happens at the endpoints? The limit must exist as we approach from the right or the left. Okay, that doesn't mean the overall limit exists, right? Just like here, because the limit from the left does not equal the limit from the right. But the two limits are existing, right? So, okay, so that is the function that is piecewise continuous. So we do allow some breaks in the function. And we've already been working with some functions with some breaks. Remember the parachute problem that we looked at before? We had one equation for when before the parachute opened and another equation after the parachute opened. So we've already kind of been looking at piecewise continuous functions for some things. Okay, so second thing we need is that the function should be of exponential order. That means that it doesn't grow faster than an exponential function. And so therefore the function is bounded by some exponential function, some constant times e to the at for all t greater than t naught. And so just as a quick set of examples here, all bounded functions are of exponential order. Why is that? Well, you could just set the a equal to 0 in that case, right? And then you would just have your f of t be less than or equal to m, right? That's what it means to be bounded. Good. So all bounded functions like sine and cosine are automatically of exponential order. All polynomials are of exponential order, and that's because of a little trick that we can use to see that. T to the n you can rewrite as e to the natural log of t to the n. The n then drops out in front, and so now we have an exponential function. But this natural log of t is, we want just a t there, right? And as it turns out, the natural log of t is less than or equal to t for all t greater than 0, which is easy to see graphically. and it's not too hard to prove. In fact, we'll leave that as an exercise that the natural log of t is less than t for all t greater than 0. Here's a hint. If you have two functions, f and g, and and f of a, for example, is greater than g of a, and then you have f prime of x is greater than g prime of x for all x, then what happens to the two functions over time? That's something called the racetrack principle. That might come in handy for that. Okay, so not an example. What is not of exponential order? So if the function has to blow up faster than an exponential function, so it's probably easiest to think about this at here. I need a function up here that grows faster than a times t. So take your choice. You could put a polynomial in there, and that's what I did down here. Or you could do something like e to the t power, right? That would also work. So those are examples of functions that are not of exponential order. Okay, and so then we would have trouble computing the integral, right? Okay, so let's see. If f is piecewise continuous and of exponential order, I should be careful with this because e to the minus t squared is of exponential order, right? Because that is a bounded function. I just wanted to mention that because it's the Gaussian function in statistics, and so that is a popular function to use. Okay, so that would be of exponential order. It's just because this is a positive t squared that it's not. Okay. So if a function is piecewise continuous and of exponential order, the Laplace transform exists. And the second thing that we want to get out of this talk today is that the Laplace transform is linear. So what does that mean? Do you remember? That means that the Laplace transform applied to a sum is the sum of the transforms, and the Laplace transform applied to a constant times the function is a constant times the Laplace transform. Now, these are actually pretty easy to see when you realize that the Laplace transform is just an integral, right? So how do you integrate a sum of two things? Well, you can integrate each one separately and add them together, right? So the integral of the sum is the sum of the integrals. Similarly, the integral of a constant times a function is a constant times the integral. Okay, and so we're going to use the property of linearity in order to compute some linear transforms. Let's see. Laplace transforms. Did I say linear? I need more coffee. So Laplace transform of 3t minus 2e to the 3t plus 5. We can break up the transform into pieces and take the Laplace transform of each piece. And there we go. So that's pretty easy to do now. So this is, again, why I say to have your table next to you when you're doing these, so you can get practice looking things up on the table. Okay, good. All right, so now that we have the transform, we need to be able to invert the transform. So that means go from a function of s to a function of t. Now, instead of actually defining what the inverse Laplace transform is, it actually is a complex integral, and so we're not going to do it. We're just going to assume that it exists. The inverse Laplace transform is linear, and then the table of transforms is going to be used to do the inversion. Okay, and so let's see how that's going to work. For example, f of s is s over s squared plus 4. What is f of t? Well, let's go back to our table here. Quick as a bunny. Where is it? There it is. Do you see that anywhere on the table? I think it's number 5, right? S over s squared plus 4. And so a is equal to 2 in that case. And so the transform will be cosine of 2t. Oops, sorry, now I gotta go back to where we were. There we go. So f of t is cosine of 2t. Good. And so there are going to be lots of more examples. We'll put some examples in the next video. See you then.